Hi everybody, welcome to another DWF video. I'm going to start again a long and mostly useless project. And here I have the first item needed for this project. Oh nice, a little printed hardware configuration. But yes, this is a 5¼ inches floppy disk drive. Looks like it is a new old stock one. It even got a silicon gel packet, very nice. This drive is a TCFP501 and it's a single-side dual-density drive from 1980 something. It still has the protection card that was installed for shipping. Indeed, it looks very clean, almost as new. I'm sure everyone is wondering what would I do with a 40 years old floppy disk drive in this year 2024. I still enjoy using my old computers for various tasks. The Apple II, for example, has a nice compact footprint with 2 disk drives sitting under the monitor. When I need or want to use the Commodore Pt, however, the space constraints are much higher. The 3040 dual drive could indeed live under the computer, but that makes a very inconvenient setup. Most of the times I still use the tape drive too. Of course, small single-unit floppy drives with the IEEE-488 interface do exist. However, they are quite rare nowadays, and prices of everything with a Commodore logo have reached ridiculous amounts, at least in Europe. The SFD-1001 was also a very good option with its quad density 100 tracks per inch mechanism, but it's even more expensive than the 2031 when it appears for sale. The 1001, however, is not read or write compatible with the format used by the 4040, the 2031 and 1541 disk drives. Another option would be converting one of the serial IEC interface drives, like one of the 1541 family, to the IEEE-488 interface. This is almost straightforward, both on the hardware part and on the firmware part, and I'm sure I've seen the conversion kits for sale on the web. However, I've sold all the drives I was not using some years ago, so all I've left are my original 1541 and an older one that I use most of the times with the C64. If I really wanted to attempt a conversion, I would, however, prefer either a 1541C that got a track 0 sensor or the very compact 1541-2. What everyone else uses nowadays is probably some incarnation of an SD card adapter for the IEEE-488 interface, like this one. However, I'm not a big fan of these modern adapters. I really like using the old floppies, and by the way, most of my old ones can still be read fine after all these years. Floppy disk drives are, by the way, one of my favorite computer peripherals, second only to modems. In fact, back in the old days, I bought this book about the 1541, which included also the schematics of both the long and the short PCB versions. This is a 1984 book, and at that time it was really amazing to find schematics of this kind of devices. Remember that we had no internet in those years. Also, this book had the all disassembled 1541 firmware with comments. I'm not sure how they could get that code in 1984, but it was really useful for some of us. So, attempting to make a complete disk drive for the Commodore Pt is probably the best way to learn things I still don't know about how those old drives really worked. Sometimes useless things are the most exciting ones. I wasn't really looking for any particular drive brand or model. I did, however, look for a single-side 48 tracks per inch drive to make a 2031 compatible unit. I could, of course, use a dual-side drive with head 0 permanently selected, but the real single-side drives are usually more reliable. Another very important thing is being able to find the service documentation for a drive we want to play with, because I was sure from the beginning that I would need some hardware modification of the drive electronics. Commodore and Apple did not use the Sugar interface for quite a few good reasons. So, since I could find both a service manual and a readable schematic, I grabbed that drive. It wasn't really cheap, but also not as expensive as the usual prices of the older Tandon TM100 or the Sugar SA400, for example. Another interesting thing about the FB501 drive is that it was used on the Commodore compatible MSD SuperDisk drive that had both the IEEE-488 interface and the serial IEC interface. However, this fact didn't give me any more preference to the choice. Of course, the first thing to do is make sure the drive itself works as intended, but on the first visual inspection I've spotted this electrolytic capacitor with an evident oxidized leg. That means its electrolyte solution leaked on the PCB. After removing the capacitor, we can observe some corrosion on nearby component pins, but I think the solder joints are still good, so I'm not going to touch anything yet. However, we can also notice black marks on the solder mask running over some copper traces, so I have to make sure the traces are not interrupted. In these cases, I usually remove the solder mask with a sharp knife and then apply fresh solder over the copper traces. I did the same on the other traces that showed the black marks, but no trace was yet interrupted. And yes, there was almost no capacitance left in this leaky capacitor. It was originally a 100 microfarads one. I've also substituted other two capacitors with same brand and value, even if they showed no signs of leakage, but left alone all other capacitors on the board that were testing still fine. Now it's time to remove the Spindle motor PCB, because I want to test the capacitors on this second board and inspect the traces. To do that, I must first lift the spindle rotor, and I removed the 3 screws holding it to the motor body, and then marked the position of one hole with a pen. In this way, I can reassemble the motor in the exact position. It's maybe an unnecessary step, but it's always better to put things back in the original place if possible. After lifting the rotor, we need to remove 3 more screws. Then we can carefully lift all the spindle assembly, rocking it from 2 opposite sides, like this. Now I can inspect the traces and measure all the capacitors ESR. In this case, every capacitor showed good low ESR, no traces showed any corrosion sign, and there were no signs of leakage. So I just reassembled everything and I'm now ready to test this floppy drive. Another important item I needed for this project is this one. It is a device called Greaseweazle, and I have added a link into this video description if you want more information about it. Basically, it's an USB device that allows connecting and using a floppy disk drive, reading and recording the magnetic flux transition intervals. Now I'm using the RPM command to start the spindle motor. However, this tool wants to see the index pulses, so we need to insert a floppy into the drive. Now we can check the spindle speed both by the help of the Greaseweazle program tool and by visually observing the strobo pattern that must appear still when illuminated with an old incandescent bulb. The pattern for 50 Hz mains is the inner one, and indeed it looks still. If necessary, on many floppy drives the spindle speed can be adjusted by turning a small trimmer like on this one. On a single-side drive, the floppy surface read and written is the bottom one. And this lateral notch tells the drive that it's okay to write on this disk. In fact, the notch goes right under this optical sensor. Then we have another optical sensor that looks for the so-called index hole. Which is this one. However, the other side of a floppy disk can be used too, and we did in fact flip the floppy upside down to use it. However, in this way the index hole is in the wrong position. Also, we needed to cut another right enable notch, like I did on this one. We could flip the floppies upside down because Commodore and also Apple drives did not use the index hole at all, and everything worked fine. However, we must make sure that our drive is not using the index sensor pulses for the spindle motor speed regulation. I haven't seen any 48 TPI drive that does that, and I'm sure also this one doesn't need the index pulses. But this is easy to test with the Greaseweazle, so let's do it. This time the floppy goes upside down. I'm telling Greaseweazle to read a Commodore 64 image generating a fake index based on 300 RPM spindle rotation. We can observe the 50 Hz inner strobo pattern that appears still under the incandescent lamp, so the speed is correct even if the drive is not getting any index pulse because of the upside down disk. However, we are getting a lot of read errors on this disk, but I'm not yet worried about that, since I picked this floppy randomly and we still need to talk about head alignment and stepping. Now, at this point, things start to get interesting, and we may discover that one particular drive mechanics that we want to use for a Commodore compatible drive is not suitable. Let's understand first how the original Sugar interface handled the head positioning signals. As we see here, directly from the FB501 service manual, we have two signals. One is called direction and the other is called step. When the drive sees a low pulse, then it will move the head assembly by exactly one track distance, inward or outward, depending on the logic lever present on the direction line when the low step pulse happens. Now, this full track step thing is a rather crude method. It means that drives must be always perfectly aligned with each other if we want to share disks between different drives. In fact, as we can read in this text, taken from the Commodore 51 troubleshooting and repair guide, in reality the actual step motor in the drive mechanics is able to step by half a track distance, and the control electronics will make two consecutive steps to move between adjacent tracks. Commodore used drive mechanics with stepper motors that can rotate by 1.8 degrees on each step and need 3.6 degrees of rotation to move between tracks. The firmware will try to move the head half a track distance in case of read errors and try reading again the same sector, and in practice this trick works very well and allows sharing floppies between not perfectly aligned drives. Now, luckily, the TCFB501 head stepper motor is also the 1.8 degrees per step type, so one way or the other it can be adapted to move by half-track distances as needed for the Commodore drive firmware. However, not all 48 TPI drives do have that kind of stepper motors. Here, for example, we can see a Panasonic drive motor that does 3.6 degrees per step. Such a drive could be still made to move at half-track distances, but with a lot more effort. If you want to make a similar disk drive project, make sure you carefully read the service manual before deciding if a drive can be adapted easily or not. Now we need to understand a bit better how a stepper motor works, at least at the electronic drive level. Such a motor does not run continuously whenever a current flows on some wires, but rather it makes a precise step rotation when some internal coils are energized in the right sequence. The TC drive stepper motor is a unipolar type. It means it has two sets of coils, each with a center tap, called COM in the schematics. The two center taps are usually connected to a power rail, for example the 12-volt positive supply. Now, if we want to rotate the shaft by the nominal rotation degrees, in our case the 1.8 degrees nominal step, we connect one coil tap to the opposite rail with respect to the common one, starting from the A1 and going in the correct order. To rotate in the opposite direction, we follow the step order backwards. So, for example, if we are in the number 3 configuration with the tap C energized and we want to step back, we energize the coil B. If we want a step forward, then we energize the coil D. Notice that the sequence repeats after 4 steps, of course. However, there isn't only one phase configuration to make these motors move. Here we see an alternate full-step phase sequence where two coils are energized at the same time. With this phase sequence, the motor will also move by the nominal rotation degrees at each step, but will be capable of more torque because of the additional current we are now feeding into it. And now things get even more interesting. The two phase sequences that we have just seen will result in the same step distance but with exactly half a step offset between the one coil sequence and the two coils one. So if we combine the two sequences, we actually get the so-called half-stepping sequence. Using this phase progression can make a 1.8 degrees motor actually move in 0.9 degrees steps. This also means that we must first check what type of phase sequence the control electronics is using on the drive we want to modify. Let's first look how the stepper motor phases are driven in a Commodore 2031. A Commodore 1541 will work in the same way, but usually with different components. The drive firmware only uses two bits called STP0 and STP1, so they can take 4 different values, exactly how many different configurations we have in a full step sequence. The STP value is incremented by 1 by the CPU drive to move the head by half a track up, or decremented by 1 to move the head by half a track down. This also means that the full track positions will be only at values of 0 and 2. Now, the 74LS139 IC will transform this 2 bits value into one of its 4 outputs going low, and the combination of the 7406 gate and the transistor will ground only one motor phase for each of the 4 possible STP values. The two center taps of the motor coils are connected to 12 volts, so these drives use the standard unipolar single coil phase sequence. Stephen Wozniak did an even wilder choice when designing the disk controller for the Apple II. As we can see, the stepper phases can be driven directly from the CPU data bus via the 9334 addressable latch, so any kind of stepping sequence can in theory be implemented, even some very creative ones. Now, for a little experiment, I want to check on a real 1541 what are the stepper wire colors and what is the correct phase sequence. I'm going to use a program called Exerciser, found in the Troubleshooting and Repair Guide. This program allows positioning the head at any half track by incrementing or decrementing the STP value. Then I measure the actual voltages on the STP bits and on the wire motors on each of the 4 possible phase configurations. So at the end I could write these notes. This will help me for the next experiment I'm going to show shortly. Now, on the FB501 drive, all motor and stepping functions are handled by a little microcontroller unit. So, to understand how it's driving the stepper phases, I can only check with the oscilloscope or the multimeter on the motor wires. I'm checking 2 wires at the same time during a complete disk read. What we can see is that 2 phases always vary their voltage at each full track step. I'm trying all possible different wires pairs. So, to make a long story short, here's what I've learned by reverse engineering so far. On the left, I have the track number and right to it the voltage on the motor phases. So actually the zeros in this case mean energized phase. It is clear that this drive is using the high torque drive, since 2 phases are always energized at the same time. Also, we can see that the phase pattern repeats every 2 tracks, so this is a confirmation that the electronics is actually making 2 steps for each track interval. Another thing to notice is that the MCU connects the 12-volt rail to the central motor taps only during the phase changes, but when the head is not moving, the central taps are connected to 5 volts. This is probably a method to reduce the total current consumption of the drive and avoid the stepper motor overheating. However, I'm still missing one important information. What I have seen is the steps with the green marks. Notice that we don't know the correct step direction, because if we are, say, on step number 3, we can move backwards to step 1 or forward to step 5 that have the same configuration. But in the first case, we need to go first to step 2, and in the second case, instead to step 4 that have different phases energized. The intermediate steps are not easy to capture on my analog scope. So let's try another method. I have disconnected the stepper motor from the 1541 drive and instead connected the drive electronics to the 501 stepper motor. And now I try stepping with the usual program. I am incrementing the track number, but the actual head movement is going backwards to track 0. So I connected the phase wires in the wrong order. So with the phase wire inverted, I think this time it will work in the right direction. And yes, incrementing the track number now makes the head go towards the disk center. Oops, I think that we hit the stop here. Decrementing the track number makes the head go back to the lower tracks. That's very good. Now I have the complete picture. With the 1541 driving the stepper motor, I can of course measure the half track's phase activations, so I could feel the missing phases for the high torque stepping. And I can do this because, if you remember, if we combine the standard full step phases with the high torque ones, we get the half stepping sequence. So I have 4 activations I can measure with the 1541 and 2 I can measure with the original drive, but the missing 2 steps must follow the order on this table. In this way, I can have the complete picture with 8 phase activations that contains also the original high torque sequence. Now, how can I make this drive step to the half track positions? Well, one possibility is playing with these jumpers that, however, are not documented in the service manual. Since this controller is the same used on the quad density 80 track versions of this drive, probably there is a jumper configuration that makes the CPU step each half track in response to a step input from the interface, as if it was an 80 track drive. However, such a modification would also require me to modify the Commodore disk firmware to produce a direction and step controls instead of the 2-bit step sequence that we have seen. Since I don't want to change too much on the drive firmware, I decided that I prefer bypassing the CPU entirely in this case, and drive the inputs of the IC that controls what phase wires get grounded. So the first modification I'll do on this drive is to add a socket on that IC. In this way, I can plug the original IC back into the socket and the drive will work normally with the Sugar interface. Or I can insert a little dado board on this socket that isolates the input pins of the driver IC and brings them with a cable to the new controller electronics when I will have one. For a read test, I'm going to use this original 1541 demo floppy disk. I haven't cut any right notch on this one, so I'm sure it still has the original factory formatting. It's not like a reference disk for head alignment, but it's better than a random floppy disk formatted by a random drive. I'm going to use the Greaseweazle tool to read and convert the data on the fly for the 1541 format, so it will check that the sectors are decoded correctly. Track 1 seems to have a few unreadable sectors. That may well be the case on a 40 years old floppy disk. However, most of the rest of this disk is being decoded correctly. At this stage, I'm not worried about any alignment issue. That will be the last thing if and when everything else works. I only wanted to be sure this drive has no evident faults. As a last test, I'll erase a few floppy disks and write a D64 image file on them. To erase and write on the flippy side of the disks, I'll use the fake index option for the Greaseweazle tool. This will rely on the spindle speed to be exactly 300 rpm. And let's see now if the floppy written before can be read in my 1541 drive. The directory loads fine, but let's try something better. This simple program will basically read all files present on the disk to reconstruct the block allocation map, but that's faster than loading every program from disk. I've written 4 disk sides and all of them show no errors. This disk instead was written with another drive that I misaligned by about half a track on purpose. The 1541 can still read many tracks correctly. But eventually it fails on inner tracks. Now that I'm confident that the disk drive I've got has no evident faults, let's quickly see what are my design goals. Of course, I want the drive to be able to run the original 2031 firmware, even if I don't plan to use the unmodified firmware as the final one. For instance, the original 1540 and 2031 firmwares produce some differences in the disk format with respect to the 4040 dual disk drive. These differences are described in this web page, linked in the description down below. These differences have been mitigated in the newer releases of the 1541 drives, but it seems no new revisions of the 2031 firmware can be found. Other than that, I really want to add support for the track 0 sensor of the drive mechanics to avoid the head bumping into the stop every so often, and then have the head go back to the first track when the drive is powered on or the CPU gets a reset signal. Another thing I really want to add is starting the spindle motor whenever a disk is inserted, like it's done on the 1541C and 1571 drives. This is important to allow the clamp to center the disk correctly when closing the latch. In fact, even before the 1541C, the SpeedDOS ROM for the 1541 that many of us installed back in the old days would start the spindle for a few seconds after a disk insertion. And even this big 8 inches half-height drive starts spinning as soon as a disk is inserted. Most of the older 8-inch drives had AC spindle motors that were always spinning whenever the drive was powered on. And last, if possible, I would like to add some improvements, mainly because that could be useful for hacking or experimenting. So I plan designing more RAM space than the original 2 KB, the possibility to select at least 2 different firmware images, and the possibility to have a faster data clock to experiment with higher density disk formats. So I started designing the controller part. Of course, it has to be enough similar to the real 2031 to be able to run the unmodified original firmware. When a prototype is ready, it will be the topic for the second part video. I've also started working on the firmware part. This will take some time too, and likely will be the topic for another separate video. At the moment, I have no roadmaps or deadlines. I've got quite a lot of hardware from other persons that I need to repair, so that will get most of my spare time before I can progress with this project. I hope this video was interesting and that you learned something. If you have any question, please use the comment section below. It's all for now. Have a nice time and thank you for watching.